Where were we on things? Y'all remember? I don't think we got to the gas phase equilibrium constant stuff. Let's see if I can find it. 26. This one? I thought we got two.
I was just viral.
Get those. Oh, but not. Probably not this equation yet. Okay. All right. Give folks a trickle in. Got to thinking about when are we doing exam 2, right? Because the 2 lecture slides that I have open here, that's it. So could be as early as week from today. Probably not earlier than that. What are y'all's thoughts? What else is coming? I guess we have next week and the week after before spring break. Is that right? Don't look for me. See, I'll make sure I'm calibrated. Make sure that's correct. So we have 3 weeks counting today. And spring break. Is that right? We have 2 weeks counting today, and then there is spring break. That is not what I thought. Was in fact, no. All right. So this, I'm going to address Allison with this question, but it is open to everyone for input. Allison, I am thinking that we definitely need to do the exam before spring, because letting it sit across spring break.
Don't worry about it.
Oh no, I got things from the word about over spring break. I got pH from the word about over spring break. So, well, start thinking on it. Start sending me ideas and Allison ideas. You got your Discord, did you say? She got her Discord thing, so y'all start sending her stuff on that so she can pressure me to put the exam some particular time. How are we going to do much better on this exam? What are you going to do? Kiara, you were talking about going to the math lab, right? And that's been helping. Good. What else? What else could you do? Say again. Okay, yeah, you mentioned that. Oh, let's look. I want to make sure. So you can see them? All right, I think this is homework 7 worked, homework 8 worked. I think y'all should now be able to see those. Then I'll have to make an equilibrium 2. Probably do that this evening. Get it up for you so you can have it turn in by tomorrow night. Where do you feel like you are on the homeworks now, Dave? Let's see. We want to discuss the old ones first, the rate law stuff. Say again. Rate laws? What do you want to know about them? So do you feel like, let's see, if we look at those, do you feel like you're okay with those? I hope y'all are looking at these, right? If y'all are not practicing these, yeah, it'll go poorly again on exam 2, right? So you've got to get in there and be practicing these. And also, I am not opposed to cramming right before a test. I think it is bad advice to tell students not to do that. I think what people are trying to accomplish, though, is they're trying to accomplish, well, also don't wait, right? So be caught up beforehand and also cram for the test is what I'm thinking. Any thoughts on this? Anything I need, anybody know of anything on homework 7 that I need to? Or homework 8? Was this one? Yeah. So number 10, that's no correct answer. So when you steal these, right, this happens. I forgot to change these answers, the answers on here. And this question actually is one of the things that caused me to abandon doing the Georgia View quiz because of this question right here. So what I was seeing was a normal fraction of my classes were getting this question right. Well, then when I go and work it, there's no correct answer. So how were they doing that? Well, it turns out that this question, you can just copy that question stem up there, and Google it, and it'll come up with the chegs and stuff like that. I believe this was cheg, but it might be one of the other ones. And it's there. And it chooses, let's see, which one did they want? They wanted, I'm pretty sure that they wanted this one right here. But it's off by 3 orders of magnitude on the K. But the answer was there in check, and so normal percentage of people were getting this one, quote, correct, right? And that kind of told me what everybody was doing. You can't get that. So, so you should be working it out this way, and I got it set up there how you could work it out and get a correct answer. This one was stolen from, where is this? This question came from originally, I think from Chang, not sure of that. No correct answer. All right, well, I guess y'all should be on the next one then, right? Oh, and you were saying you did do this one? Oh, not that one, not acid yet. Oh, go ahead, do the preview. This one? These down here? Yeah. Okay, tell me about where you're at with them. Okay.
Question 2.
So you feel good with question 2?
Yeah.
All right. So what are you going to do with question 3 then? What is question 3 about? Anybody? Everybody else throw in with it yet? It's y'all's homework too, which y'all should have already like attempted, right? Yeah. Do what? Yeah. So how are you going to decide it, right? What are you going to be looking at to decide which way it's going to go? Okay, so you got to calculate the Q for each of those, given those concentrations, and then also compare it to the Q. Okay, and what are you looking for? So if the Q value is above 17, what's it going to be doing? Yeah, it's going to run backwards. I agree. It's going to make more reactants. And if the Q, calculated Q is below 17, right? Yeah, that's the idea. Okay. All right. I think that's all there was in there, right? I mean, it says, questions 2 and 3, but question 2's got 2 points, but 2 parts, and question 3's got 4 parts, so it's a little more than it looks like. All right. So y'all remember how the equilibrium stuff works, right? You can calculate as Q's, you can look at a K. How are the K's calculated, or the Q's for that matter? How do we set up the equation for them? Okay, K is Q when it's at equilibrium, and how do we have an equilibrium expression for that? K equals?
It's the C of X above, C of X, D of Y above, A of something, B of something.
Okay, so the concentration of all the products divided by concentration of all the reactants. Okay, Well, that discussion had all of your species behaving themselves in aqueous solution, which is where we like things to be. But unfortunately, that's not how things always are. They're not. All of your reactants, all your products may not be aqueous. Now, the K also works for gaseous reactants and products, and I think that's where I want to go first. Remind myself here where I want to go. Okay, so I think y'all would see how this works, right? What would you do? What would you do for the top one? What would be your Q expression for the top one? Wait, no. All right, maybe we should do this. Brandon, would you flip on me a light over there, please? That front light that I hate so much. You know, the bright one up here, so everybody can see. Try the middle. Yeah, that works. All right. You what? So how are we going to write that for the top one? For, let me scoot it down a little bit so I got room for it. So we've got HF, AQ plus H2O, L, back and forth to H plus. So they put H3O, same thing, H plus, AQ plus, F minus. All right, so what's my Q look like here? Come on, y'all, you cannot lose this over the weekend. You gotta still have it. Good. Does he want the next one? Okay, wait. All right, let me set up a new one for a second. Let me set up this not up there on the screen. Let me set this one up. What if I do this? Let's do a gas phase reaction. HF G plus H2O G. Yeah, I better change this to H3O. The reaction I'm about to do. Make more sense. Okay. Now what's this one look like? Q. What's my Q gonna look like here? Okay. Now, why have I done it differently? Why would I put H2O in the bottom one and not in the top? But okay, because these guys, what's this phase here mean? What's this phase notation mean? Dissolved in water. Okay, and so we normalize it, water dissolved in water. We're just going to call one. That's why it's not here. But here, that's not true. The bottom one is gas phase reaction not dissolved in water. So in that case, you would impact it. Okay? So there's not this automatic thing. Well, if it's water, I don't include it. No, not a true statement. Does that make sense? Depends on what's going on. You've got to look at it more. Use your actual human intelligence. Don't be an AI. All right? All right. So we can find now at equilibrium, this guy will be your book calls it K sub C. I usually say K, Q, but we mean the same thing. Okay, but now this one, the gas phase, it uses a slightly different terminology, K sub P. And the P that they're using there refers to pressure, or partial pressure of the gas phases. Okay, now, one big thing here is if you look up the K, for a reaction, you need to know what the conditions, what the reaction is, what the balancing is, and importantly, what the phases are. Because if you look up this reaction, HF, dissolution of HF in aqueous solution, you're going to get a totally different number than if you look up a gas phase equilibrium. Okay? This happens in multiple places. I'm going to talk about this in a couple of places. Biologists, this is going to matter to you because when you do protein work, okay, biochemistry sets up a whole different system. Their normalization is not the same as ours. One of the big differences they do, we normalize to 1 molar H plus. That is pH 0. Okay? They don't think pH 0 is really a thing for biological systems. Most things die at that. So instead they normalize it to H plus concentration 10 to the negative 7, which is pH 7. Okay, which is a more normal system for biochemistry. So be aware of, like, if you look up your K values in a biochemistry textbook, totally different. Okay? Also, chemists, so then when you go on to P-Chem specific, okay? P-Chem specifically is going to talk about equilibrium mostly in the gas phase. Okay? And I know Woz loves an experiment where he does the dissociation of HCl, like hydrochloric acid, but it's not really. It's molecular HCl in a gas phase. And so you're looking at a whole different scenario than if you have water molecules. Okay? Okay, now this setup, the way it's set up still works the same, okay? The difference here is instead of concentration of product C, we're going to be using the partial pressure of, but we're still going to raise it to the coefficient on that just like we would normal, okay? Does that make sense so far? And the K works the same way. So I guess the take home from this slide is the only difference here is we're replacing where we had concentrations for an aqueous equilibrium, we're replacing it with partial pressure for a pure gas phase equilibrium. Okay, that's the only difference. It's about to be another one, but for right now, you see that. That's sinking in okay? All right. A really easy question to ask on a standardized test would be, here is the K sub C, calculate this in K sub P, or vice versa. Here's the K sub P, calculate the K sub C. Numerically, they're not the same, but they are related by the ideal gas law and its constants, okay? That's what we're gonna do, we're gonna relate those two. So a really good exercise in picturing what's going on in these equations. This is one where I thought through the process of, you know what, likely to be 1 or 2 questions on a standardized test. I could just triage it and not bother with, but I kept it because I think it's a good exercise to look in there and try to deconstruct an equation in your head and see what's going on. So you want this equation right here, the pressure-based equilibrium constant is equal to the concentration-based equilibrium constant. Multiplied by, and here's where it gets a little complicated, this is the ideal gas constant R times your temperature in kelvins raised to the delta N. And that delta N we need to look at and see what they're doing. It's basically, the idea is it's the change in the gas phase molecules from one side of the equation to the other, or you could say the molar ratio from one side to the other. I think an example might make this a little, I'll come back to this in case anybody wants to see it again after we've seen an example. I think that might make it a little better. So this example up here, how many gas phase molecules do you have on the left? 0, because it's solid. How many gas phase do you have on the right? 2. So your delta N would be positive 2. Okay? So that's the idea here. So then what you're going to do, once you find your delta N, then you're going to go back to this equation right here, and you're going to plug it in. Let's look again at the example I have up on this one. So I've got that, we've seen this equation before, the 1 N2O4 molecule, basically it splits, and it makes 2 of these NO2, nitrous oxide gas molecules. Now, in this case, what do you want to call your delta N up there? Marcy, what do you see? Your instincts tell you. Not making sense? Can you back me up to where it did? Talk to me, or I need to go back to. Changing gas phase. Sydney, what do you see?
Use the number of bonds.
I agree with that. That is a true statement, yes. So in this case, they're all 1s, right? Yes. Oh, no, I'm sorry, they're not. They were all 1s on the left, but they're not listed. So close. So you do use the 2, but don't ignore the 1. Okay? So it's the change in. So it is true that you have 2 now. Sorry. Therefore, delta N here would be 1. Does that make sense? So the gas phase is amongst all of your products. Subtract the gas phase amongst all of your reactants, right? And in this case, your products, there are 2 gas phase equivalents, and there's 1 reactant phase. So my delta N is 1. So what I would do is I'd take the Kp, right? Or I'd take Kc in this case, and we're going in that direction. To calculate the Kp, I would take the Kc, and I would multiply it by 8.314 joules per mole K, right? Times whatever temperature, what temperature are we at? Okay. Let's say 300 to make our math easy, right? 8.314 times 300, right? What is that? 25-ish? Somebody help me, I'm trying to do math in my head. About 2,500. There would be in joules. But no, yeah, that's a good question. Next question, what do you do here? I think it washes out because of the unit canceling shenanigans we do with K. And the K sub E is normalized to 1 bar of pressure, and in case of C is normalized with molar concentration, so you get a Henry's law, that's it. It's Henry's law calculation. I talked it through to get an answer for you. Wait, this one? Well, this one's got liters per mole, so maybe let's use this one. That does make sense. Your unit question, very good, Brady. So look at what he's done here, y'all. He caught me. I was going to use the 8.314, but because this constant is gonna catch the liters in the atmosphere, I think Braden is on a better path here. Let's use 0.08206 liter atmospheres per mole K. I think I like that one better. So then what's my R times T here? Say it's 24.6, okay? And we're raised to the first power, so we're gonna just keep it 24.6, okay? So your K sub P is gonna be basically 24 times the size of your K sub C, okay? Alright. That ends last week's, last Wednesday's lecture, and we'll move on, and that was the only thing left, was the K sub P calculation, okay? So I'll make sure to throw some of those on the homework for practice. Braden will remind me to use the 108, 206, right? Thoughts before we go on? One of the things that Allison may even get excited about, because most chemists love what's coming in this, right? You do? Okay, most of us do. Most of us do. What's coming, Allison? Yeah, with a what kind of table? Ice tables. All right, ice tables are coming. All right. We love these things. Just did this. Practice problem for this. Let's see if we can get there. Somebody, I don't know who, was it this class, told me that they would like to see me walk through my thinking. Was it? Okay. We'll do this one together, but I want to give everybody a chance to play with it for a second. Remember that you have these slides, so you can look through. Oh, there's not a team call. I tried that, and it worked once, and then it didn't. And I decided to quit fighting teams and give up. Give it a shot. Remember, you can get to these PowerPoints and these questions, so you don't need to write the question down. Now, a plan of attack. Anybody want to start me out, or y'all? What do you think?
Use the K of P equation to find K of C.
I think we can ignore KC in this case. What would we be using the KC for?
To find K of C to get to the.
Well, we've got the KP, let's just use that. Because we've got, let me get a highlighter here. So we got partial pressures, right? This is in pressure. This is in pressure. And then what's it looking for? Oh, and it's looking for partial pressure. Hey, our whole problem was in pressure. So let's just stay in KP. Yeah. So don't spend your time trying to calculate a KC here. We can do it, but I don't think we need to. I would check this first to see if it's balanced. Y'all happy that it's balanced? It is balanced. Okay. I got ones. All right, cool. All right, let's see. Now my KP expression here, this is where I would be thinking to start with. Like a KP expression is set up with, how do we write the Q's or KPs here? How are we going to do that? Yeah. So what goes on top here?
Pressure of ECO3.
Yep. PCl3, PCl3, right? And
The pressure
over partial pressure of this guy. Okay. Do we have any of that data? Oh, we do. Oh, okay. And we know that it is equal to K sub P here is 1.05, and it equals, let's see, what do we know? We know PCl3, 0.875, and we know, we don't know PCl2, right? Where are you at? Oh, is that right there? Okay, good catch, good catch. This one? What is it?
0.463.
Good. And then this guy, so I had some lines. Okay, so let's solve for this guy. What's it gonna look like? I don't want to do that one. RC, making sense? So again?
1.9.
Beautiful. Good to see you, Chelsea. Okay? Happiness? Review here. Get rid of the light. All right, what do y'all see in this one? What jumps out at you here? Anything come out at you? How about my phases? Talk to me about phases here. Okay, it is. Does that do anything for us specific? Is there anything magic about that? Yeah. This is one of those situations. Everything else is aqueous, right? So water is not going to be part of our calculations. Good. All right. Assuming there's plenty of it around. You're going to use that right there, okay? I think it's set up. Now, if they're in different phases, once you start mixing things, these are some of the complications. Obviously, some of the places we'll ask questions, right? So, you're already talking about the liquid, the water, not being included. So, if your solvent is most of what is there, you can zero it out, basically. You're dividing, so you don't want to go to 0, you want to go to 1. But you can normalize it to 1 because it's solvent, concentration of solvent. Okay? So, but that happens also with solids. In this case, yes, so. Say again. Here, 1.9 atmosphere. All right, Mercy, check your other votes, check them.
Yeah, 1.9.
Oh, sounds like the chorus going. Are you seeing what's happening? We'll walk it through step at a time later.
I don't know what happened.
Okay.
I just thought that was all.
Okay.
For some-
All right, beautiful.
but that didn't happen.
All right, so, well, looking at this one, okay, your intuition might be to put calcium oxide on top times CO2 on top divided by calcium carbonate on bottom. But the trick is that those are solid phases. And so solid phases, we do this normalization things, right? So we're talking about the concentration of calcium carbonate in calcium carbonate. So that becomes a 1. But what we do in this case is we make those a 1. And so our Kc, just CO2. Huh? Okay, all right, well, so the prime up there, the middle row. So the calcium oxide, see, it's a solid. So it's we're gonna just treat it as a 1, right? Agree? As long as it is in equilibrium and it's still there. Yeah. Yes, no, definitely not. Yeah. It's okay if there's a coefficient. That's not what changes. It is whether or not it remains a solid in excess throughout the entire reaction. If it does, then we treat it as if it's a 1 in the equation. Okay? And that leaves, in this case, only the CO2. I've got a graphic with this that might help explain how that would be the case. Okay? Yeah. All right. This is a graphic trying to explain, because Miriam is balking at that a little bit. She's thinking, wait a minute, I need to include all the pieces of my reaction, right? And that makes sense to me. But here's the one. So my little pile of stuff. Now these are both solids, right? And I guess the orange here represents calcium carbonate. And the green represents calcium oxide. The only other thing is our gas CO2, right? So partial pressure CO2. So we can measure, it's actually a thing that we can go check. We can measure the partial pressure CO2 in the system. Well, and it turns out those red lines up there show us that the partial pressure on this side and the partial pressure on this side are exactly the same. They don't care how much. In this case, there's a lot more calcium carbonate, the orange. See that? In this case, there's a lot more of the green. Well, if those were included in the equilibrium expression, it should change the value of CO2, but they're not included. As long as we've not completely run out of one or the other. If you completely run out of your solid phase, then everything changes. Okay? But as long as some still exists, then you can normalize them to 1 and leave them on. All right? Sounds like a true question on this. It is very, very common, yes. I think, Allison, have you taken any ACS exams? Okay. Taking them, Brett and I hesitate to say every one of them I have seen one of those on, but it actually might be every version of that exam I have seen one. Yes. I don't know. later. But yeah, you're right. But that's an easy thing to check, right? You gotta look for the easy way the right questions are. Hey, review for a second from Chem1212. Do y'all remember Hess's law stuff? Does that trigger memory? Remember a little bit? Yeah. What was it about? Was about good notes. Notes are good to have. Keep them for later. I've got notes in my filing cabinet from before most of you were born, maybe before any of you were born. But
reaction, even if it's not the complete reaction.
okay.
You can keep changing your products and reactants, so literally it'll be this.
Yeah. Yeah. What else? What do I do with them to do that? So. Okay. Right? Okay. So you remember how that works then? And the whole, what I'm trying to trigger here is the whole adding things together and canceling things. Percy, did y'all do that? We had to add the equations together and cancel things. You remember that? So you add all of those together, right? So if I do the line under it, to add them all together, right? You get this big long. Do we have to keep all that? Why not, Susan? What would you like to cancel out? Okay, anything else? Yeah, H2O is very impressive. Let me go, I think I animated this, let's see. Yeah, the H2Os, two H2Os, right? Yeah. There's your CO2, Sydney. Right, because you got two of them over there red on the product side, right? One and one. And that leaves us a much more simplified equation here, right? Now, how do I get the delta H's for those? In this case, you can just add them. And I want to stress that now we're going to change the rules. Okay? Now, the delta H's still do add, but for the K's, you do not. Okay, sort of like Hess's law. You can still add your equations together. Okay? So if I do this, yep.
Where's the little dash?
It's not a derivative. Fair. This is just that in-depth coding that we don't think about. Another one. K sub C, K prime sub C, K double prime sub C. Another one. That's all it means. Okay. Yeah, no, it's not a derivative. Okay, good question. Okay, so if I add these two reactions together, though, what do you get? Good. Y'all see where Braden got that? Can y'all get there in your head? Braden did it in his head, right? Add them together, it's C plus D on both sides, you cancel them out, right? Leaving A plus B leads to E plus F. And here's the difference from Hess's law, though. Because, look at K prime. So K prime C, the top one, I wish I put K1 instead of K prime now. But it is products, C times D, over reactants, A times B, and K2 there, right? But if you multiply those, what happens? C and D cancel, like Braden said, adding those reactions. So, like Hess's law, you can still add your reactions together. Different from Hess's law, right? In this case, because of that math there that Murph just said in the canceling, you need to multiply your K's, all right, for your partial reactions. Oh, there it is. I shouldn't go through the process. Cancel all those, but it's list. Okay? So the K for this would be K prime, K1 prime times K2 prime, right? Does that make sense, Mira? Yeah? Okay, now wait a minute. So hold on. Let's think this through for a second. Look at how this K is done, right? So if get another color, red. You don't see the red, okay? So if we got N2O4 goes to 2NO2, right? And you've got K, I'm gonna say it's K going that direction. How do we calculate this? What's gonna be my expression for this? What over what? Casper? Right? Yes? Well, no, wait a minute. What if I wrote it, what if going back that way? So as if it is two NO2s, right? So one N2O4, right? And it's kind of like the K of the original one going backwards. See what I'm doing there with my arrow? It would be what over what here? I'm not gonna, well, I might ask you that, but also might ask you, what's the numeric value? How do I calculate it? So up here, what's the numeric value for this one? On screen? Negative what? Okay. So how about this one then? How would you do it? Oh, okay. So we just took this, right? We took this original, how we calculated it, we flipped it over, right? So let's do the same thing. Let's take whatever the expression was for this guy and flip it over, right? That's what a -1 exponent does. Flips it over. Try it on your calculator. Put in parentheses 4.63 E-3. Close your parentheses, raise it to the -1 power, and get what? What'd you get? Be brave.
215.98.
Now let's do it another way. Take and put 1 divide parentheses 4.63 E-3. Should get the same answer. Trying it? Oh, calculator! Yay! 4.63 times 10 to the -3. Switch it. Can't find it. Have to put it. 'Where's your negative one? There. Yeah, use that. And then, okay, that, and then raise it. Yeah, raise that to negative. We got a right. All right. Does that make sense, y'all? How we did that? All right. All right, when you're writing your equilibrium constant expressions, if they're in the aqueous phase, think of them as molars. Don't forget that we get rid of the units, okay? But you want them in molar. Sydney, Merv, hopefully Miriam, y'all, that's not true. It's not molar. It's actually molar, but everybody ignores it, okay? The reason you actually do it in mole is because then the temperature independent, because you're using massive solvent. But everybody thinks of it as molar. Your book even calls it molar. Okay? Everybody ignores that. Oh, did you have questions? Okay. You can leave all pure phases like liquids, solids, stuff like that, and the solvents if they're not going away. And then the K itself has no units, and that's really important for later calculations. But you got to specify what conditions and even what reaction you're using to get that. And that this is, unfortunately, we're not really good at doing this. We should be very clear about the reaction that we're writing when we quote an equilibrium constant. We're not. Like in Harris, should. And then you can add two reactions, multiply their Ks. All right, here we go with the fun stuff. So when you want to calculate an equilibrium concentration, here's a scenario. A question might be, all right, so we take a beaker and we put this much reactant 1, reactant A, and this much reactant B, and we're going to react together to give us product C. How much A is left, how much B is left, and how much C is produced. Okay? And we're going to need a lot of calculations for this. Now, in Chem 1, we did this with limiting reactants, right? And so, if a scenario happens where you actually run out of something, then you still use a limiting reactant stoichiometry. But that's not very common. What's going to commonly happen is you're going to get some ratio of products and reactants. And then we're going to use the K to solve for some. We're going to be using a lot of algebra with this. We're going to be plugging in X's, assigning them to mean things, and then solving for them. Example. Okay, this is my first example. So y'all try this with me. So we have, what do we have? Here's how I tend to write these. I write these out. Just got a little bit shorthand. I will write my reaction, and I will write my, let's see, got 2 NO, their gas phase, plus 2 H2s, also gas phase, equilibrium with 1 N2 gas phase, and 2 H2O gas phase. Right now, be careful because the H2O here is not your solvent because we're in gas phase, right? So we do need to include it, right? Then I'll put over here. I might put, I'm not making this up as I go here. Concentration NO sub-zero. Remember what I used the sub-zero for in our rate law stuff? What did I use that sub-zero for? And then, yeah, starting condition. Do we know? 0.062. I'm gonna just put a number because we know that we're gonna use molar here, right? And everything's gonna come out as molar. I guess good habit might be to say everything in molar. That way, unambiguous. Okay. my starting concentration H2 equals, we know that?
0.1.
Oh, this is not, that's wrong. Oh, and you were here, oh, and you should have called me the break with indication, right? I need to calculate this. How do I calculate this? 1.00 moles in, okay, so what's my concentration? 0.1, okay. All right, how about my concentration H2?
0.1. 0.05.
Good. And my concentration of H2O? What is it? 1. And my concentration of N2. So what would you put? Is there any? Start with? So what would you put? Yeah. Over here, concentration NO equilibrium concentration H2, equilibrium concentration H2O, equilibrium concentration N2, equilibrium. I think in this case we know some of these. We know some in this case. Know what is what? Right. But we don't know any of the rest of them, right? Agree? Okay, well look, let's, in the middle here, how would you put that in the middle? I'm going to set up what I call an ice table, right? We have an initial scenario. We have an initial scenario, okay? And one of the reasons it's called an ice table is because you've got an initial change equilibrium. I tend to do initial change this way, and then equilibrium. Okay. So my initial for NO is 0.1. And 0. Does that make sense for y'all? What I just did? I entered my initial amounts, right? Now looking back to stoichiometry, okay? So stoichiometry, we're going to focus on this N2 for a second, and I want to call N2 my X value. So we don't know what the N2 value here is going to be yet, but I'm going to say when this reaction happens, then I'm going to gain plus X, an unknown amount of N2. Right? Now, if I start from 0 and I gain X, what do I end up with for equilibrium? X. Right? Does that make sense? Yes? Maybe? What am I going to gain? Water molecules. Am I going to gain X water molecules? I gained X N2 molecules. Am I also going to gain X water molecules? Come on, somebody fight me. Come on. No. Y'all help me. Why not? Why not? It won't be the same amount. Why not? No guarantees on that. Nope. There's no reason. There's Chem one reason. So if I gain an X in 2, what's going to happen to my H2O? I'm going to gain 2X. You agree? And so this is going to be 0.1 plus 2X, right? Make sense? Hey, what's going to happen to the reactant side? What's going to happen to my NO? We get to that in a minute. Yes, I agree. But what about my table? Y minus 2, you're correct. Y minus 2X. Yep. How about this guy? Okay, you. Now, importantly, where you were going, which one did you want to start with? We can go with any one you want. Where you know something else about. You know this one? Here, we have a value. We know that that's the expression for it, right? But we're getting information that this 0.1 minus 2x ended up at. Now, if you head over to the math lab and you find Braden and you ask, hey Braden, I got this math problem right here, 0.1 minus 2x equals 0.062. What's he going to tell you to do? Do not divide plus first, please. Yeah, reverse, yes, solve for x. When you're solving for x, you gotta reverse your order of operations, right? So you've got to, first thing you need to do here is unsubtract, right? Or unadd in this case, because the positive. Subtract 0.1 from both sides. What do you get? Negative 2x equals y'all agree? I didn't check it, so y'all agree? Somebody check it, please. You got it?
Yeah.
Got it? All right, now what? Divide both sides by negative 2. X equals 0. What?
0.9.
Good. All right, beautiful. Now, when you do this, please don't always just solve for x. Okay? Because you're not done necessarily. What is my equilibrium concentration of N2? Well, it equals x. So in this case, 0.019. But what is my equilibrium concentration ratio? It's not just equal to x, right? It's what? Nope. What's in your E for H2O? Your E line. What does it say? 0.1 plus 2x. Yes, so not just 2x. How much you get? Okay. Makes sense. So when you get here, how about for my H2? Okay? Happy? I'll remember to look at my slides for Easter eggs. Sometimes. All right. It's all worked out for you. Okay? Congratulations, you have done your first. I say, yay. Many, many, many more to come. Okay? All right, what are we going to do here? What do you want to do? I didn't even look for the Easter egg guy, right? But what would you do on your own? Practice before you get the answers, before you look up the answers in the back of the book. How are you going to set this guy up? Say again? We know KC, and we know when concentration. KP. I use KP. We didn't know KP. It does say KC. Oh boy. So we know KC. So the first thing we have to do is calculate that KP, right? What's going to be by delta N? Positive 1, good. All right. You're going to plug those guys. You're going to plug in for your initials. What are my initials here? What do you want to plug in for initials, Mary? For the I line. All right, so 1 molar for PCl5. But last part of the question stem says what? Right here. What does that tell you? Therefore, what's going to go the rest of that I line? Zeros. Does that make sense? So 1, 0, 0. All right, what are my change lines going to look like? Oh, right. What's the scale for, sir?
We're trying to keep you. What does it not matter?
Keep it with you, temperature. Yeah. So I would assume that like. Yeah, this is example 13.9 from the textbook.
Great textbooks.
So what's your change line? That's really what I wanted to focus on here. What? Go ahead. Negative x. Yeah, and positive x and positive x. Yeah, good. Right, I wonder if I just use KC. Or if I did, if I still the text I did. So, when you run it though, you get this right here. Do y'all follow the math on this? So you know, okay, fine. So we got KC x squared over 1 minus x, right? Multiply both sides by 1 minus x. That's what I did. Now in red, I'm multiplying both sides by 1 minus x. Distributing my point to my k here. Right? So I have a quadratic. Right? Does that make sense? Remember quadratics? How do you solve a quadratic? Yes, which is negative plus or minus square root of b squared minus 4ac, all that stuff over 2a. All right. Now we need to look at both options. Okay. So here's my solution. I got to go back and rework this, right? If I didn't use the KP, but okay. But when I work this through, right? Do not fall in the trap of always discarding the negative answer. Sometimes the negative answer will be the correct one. You have to check both. Okay? Now, a couple ways to solve this. Yes, you can solve any of the problems in this class just by plugging into the quadratic formula. Right? Sydney Murph for quant, not true. Okay, you will definitely need to solve. However, in this class, you are allowed to use solver if you have it on your calculator. Okay, so hold up your calculator for me. Let me see. Sydney, that one definitely has it. We should look at how that one has it. Mercy does. That one doesn't. Do you know where that one's over? That one, I think that one has it, but it's a little cryptic. So we'll have to play with it to use it. The same with those two. It's there. I think it's quite cryptic. What you got? Definitely Gloria has it on there. Okay, that one, I don't think that one has it. The gray one does. That one definitely has it. That one has it. The problem with the TI-84 series is that you do have to set your quadratic equal to 0. And Sydney holds yours up. She does not. So she can run solver without having to bother to set it up. Okay, so this one will do for you. You do not have to say equal 0. Well, 84 plus C. I think it's C over there. So what I recommend is you take your particular calculator and Google solver on and put in your calculator, TI-30X, is that right? Whatever it is. Yeah. Okay? Because every one of them is different. There is no standardization about solver works on these things. Not required to use solver. I'm just pointing it out because it might make your life easier on some of these. The quadratics have a lot of holes in it for you to fall into, a lot of traps, right? Okay. Remember then, this is not, if it comes out of solver or if it comes out of the quadratic, it's still not the answer to the question. This is only solving for x. What did x represent back a long time ago when we started doing this problem? Well, those things what was asking for interpretations, what are the equal demonstrations of each of those things. So x can go in right here and right here, but then you're going to do a 1 minus x for that guy. Okay? So x is not necessarily unique to solve for x, but it doesn't necessarily complete the problem. Okay? how much I got left. I don't have any time left to do it. I out of time, Allison? All right. I'll start working this one, and we'll finish up with this today, and we'll go back to the other. So we will definitely not have a test on Wednesday. Okay? I am open to the test being next Monday, but I might discourage it. I agree. I did that. My initial intuition, I didn't agree with. Okay. All right. Well, I will work with you if you want to preview it. Otherwise, we'll start with this slide right here on Wednesday. Okay. All right. Well, I don't know what off the top of my head. Well, I think so. 135 for PCL3, 135 for CL2, and 0.865 for PCL5. Yes. I didn't get the same thing. Multiply 0.0211. That'll do it. That'll definitely do it, Steve. Allison, what do you have planned for SI? Lots of items, okay? Which way will go? Yep. Maybe practice a little bit. Maybe you get that back to the map. The alpha is always there, right? Let's see. Class. 1 liter. So everything's in 1 liter, great. So H2 plus I2.
So that's what we
It's going to make H I. Right, to the JC is 54.3. So 0.5, 0.5. X 0.5 times X, 5 times X. Let's see. Start with 0 HI.
This.
We get plus 2X. I'm going to get 2X. I'm going to get my K. 54.3 equals 5 squared over 5 minus X squared. Okay. Oh, that's a square over a square. So I can just do square root of equals 2X.
I think, you know what?
Maybe not, because I've got 2.5 times 54 3.5 minus equal half x
Classic.
to x. So 0.5 divided as 3 over 2
I just don't have 2 to be plus and using it in English.
Then that's the number next. So I would actually the denominator first.
Let's go.
I mean, that's the one test two on standardized differential. I don't know a number, but I would say that the test is extremely important. And then here's the thing, there are probably more essays on test 3 than there are on test 6. They're going to be a big story. We're just going to use the same thing when you pass. Cindy, how we doing? Yeah? Matt's coming. Here he comes. See, one thing that, Kira, one thing you'll see, if you talk to people in tutoring about it, there's a thing called a simplifying assumption that I've not covered yet, that I will. You assume these small numbers that we use, a lot of times 0.5 minus x is 0.5. That makes the math a hell of a lot easier. Okay, so it's called a simplifying assumption. Yeah, and you know this for Miriam, like on the MCAT, if you don't have a calculator and your time, you should probably make a simplifying assumption. Now I'm going to show you places where it was bad wrong. Right? You calculate, you make a simplifying assumption, you get a pH of 3. You don't make the simplifying assumption, you get a pH of 4.9. That's a lot different. Yeah. So. Yeah.
That's why I'm doing it.
Yeah. Oh, it's so much. You learn so much. Oh. Yes. I learned so much more physics, teaching physics,
Yeah.
than I did taking physics.
If I were to continue doing a class like that, so I.
Yeah. I learned a lot of work trying to teach work. Yeah. Bye, Kara. Oh, yeah, I forgot. Okay. Thank you, Kara.
We're just hanging around.
They teach. I don't know. I hold it to you. Yeah, but I don't know if this is recorded or not. Oh, maybe. Yes, but. Oh, there he goes. Whee! Now I started running. Okay.